All right. So let me switch over here, spotlight my notes. So just remember, in terms of the big picture. So back in chapter 7, the whole goal of this, of sketching this root locus, was to hit a visual map of the location of those closed loop poles as we vary a parameter. In particular, we're focusing on this situation, the classic situation where we've got controller in series with a plant and we're varying parameter k from 0 to infinity in this setup. So we end up with this transfer function. We know our closed loop characteristic polynomial is going to be the numerator of this, of 1 plus kgp. And from there, basically, we are mapping the closed loop poles or the zeros of 1 plus kgp as k varies from 0 to infinity. So that's the goal of what we're doing. Now, we did an example where we did it manually, sort of just, little by little, and we ended up with this thing right here. We said, okay, for that particular transfer function, we had starting at k equals 0, we had the poles here and here. Then they moved inward and then they went up. And we did that manually. And then we're like, oh, can we not do that more, just in a more, just general sort of way for any type of transfer function? And so we were coming up with steps to do that. We were coming up with steps to sketch the root locus in a more general way. So the we saw that there was a 5-step process to do it. And this 5-step process had step 1 was a real axis. So starting with the real axis. And we did a few examples where we were given transfer function of the plant. And we said, okay, as k varies, what do we do? And we saw with real axis, what we would do is start from right to left. And when we were left of an odd number, we would fill that in. When we were like to the left of an even number, we would leave that blank and we would fill it in again here. We would also mark with X's. So even to begin, we would mark with X's the location of the open loop poles or the plant's poles, and with circles, as we did down here, circles the location of the open loop zeros. Okay, so that's, and we knew that the locus would always start k equals 0. They would always start at the open loop poles. So again, for this one here, we went right to left. Yeah, and we're like, okay, here we've got, we're to the left of 1, we're to the left of here where we had a double pole, so we kept going. Here we were even, and so on. So that was step 1, was all about the real axis. Now, steps 2 and 3 were about the branches and asymptotes. So here we have step 2, we said total number of branches was n, where n was the number of poles of the plant. All right. And then we knew that we also talked about those asymptotes, which is where what would happen as k was going to infinity. So we said plant has n poles and m zeros. The plant has n poles and m zeros. So as k goes to infinity, of the n branches here, m of them are going to terminate at the open loop zeros. And the rest, that is to say n minus m, are going to terminate at infinity along lines called asymptotes. And then here we found a formula for determining the location of those asymptotes. So they would have the center and they would have these angles right here. So let's, before we go into steps 4 and 5, let's do a couple of quick examples just to show you how this works right here. So let's try just a couple of quick ones. All right, so let's do a couple of examples. Let's say for each of these, I want you to sketch the real axis part of the locus. So this is step 1. Then determine how many branches are you gonna expect for this. And I want you to sketch the asymptotes. And you can sketch the asymptotes kind of like in dashed lines. So let's do a few examples here. So let's try this. Let's say we've got 3 over s plus 2, s plus 6. Okay, so try that one out. I just want you to again sketch the real axis part of the locus, how many branches, and let's sketch the asymptotes using those formulas. So try that out on your own. So let me start it out here, and y'all can check your work as you're going. So first thing you want to do is, of course, mark the locations of these open loop poles. So you're going to have one at -2 and the other at -6. Right, so that's where we start, and we know that the locus starts where k equals 0. That's where we're going to be at -2 and -6. Then, so we make sure we got that set up. Notice we've got no zeros here. We've got just this number 3 there, which doesn't really affect us in terms of the pole zero diagram. Now over here, we go right to left. And so we leave this blank. And then of course, this interval right here is going to be filled in, right? So that's going to be our real axis. And then after this is blank, right? So hopefully I can see people nodding. So that hopefully that looks good. We know then that we're going to have just this part filled in. We also know that it starts here, and then as we increase k, it's going to move this way and it's going to move this way. So we're getting away from those two spaces. Okay. Now, in terms of total branches, let's hear from somebody in the class. How many total branches do you expect here, Evan? 2. Evan tells me there's 2, and that's correct. So notice we've got over here n equal 2. We got 2 poles, and we've got m equals 0 because we've got no zeros, right? So we know we've got 2 total branches. We know that m of them end at the 0. So obviously here, none of them are going to end up in the zeros, and the rest, meaning both of them in this case, so the other 2, meaning both of them, are going to end up at the asymptotes. So for the asymptotes, we find our center and our angle. So when we do a little formula there. Center of the asymptotes is going to be 1 over n minus m. So n minus m is going to be what, 2 minus 0. Then sum of the poles minus sum of the zeros. So we've got a pole at -2 and another at -6. And if I do, so this is my formula right there, just applying the formula, sum of the poles, -2, -2 plus -6, so that's the sum of my poles, and then 1 over n minus m, so this gives me what, -4, right? -4. So we know that at -4, that's going to be the center of the asymptotes. So right here, -4. I'm going to mark -4, and that's I'm calling it sigma A. Okay. And then in terms of the angles of the asymptotes, we've got this other little formula here. Angles of the asymptotes. And it's 2q plus 1. I'll just copy it out. 2q plus 1 over n minus m times 180. Notice that for us, n equal 2, m equals 0, and then q goes from 0, 1, all the way to n minus m minus 1. So for us, that's just going to be 0 and 1, right? Right, for this particular case, because it goes up to n minus m minus 1. N minus m is 2, so just 0 and 1. So if we plug that in, I'm going to get here in my denominator 2, and I'm going to get either 1/2 or 3 over 2 times 180. So I'm going to get 90 and 270. Plugging in those numbers. Therefore, my asymptotes are going to be one up here at 90 degrees, and the other one down here at 270. Okay. And so what we can tell actually is it's a pretty similar situation to the one we did by hand, but quadratic. I guess it's so quadratic. But here we're going to have two branches that end here. Therefore, we know that they're going to break away at some point, and one is going to end kind of like parallel to this. The other is going to end down here parallel to this at 90 and 270. Any questions with that one, guys? All right, let's try another example here again before we go into steps 4 and 5.
Wait, what was Q again? What was Q in that equation?
I had a question there, but let me turn up the volume a little bit because I didn't quite hear it.
What was Q in that equation?
So Q is a counter, and it goes from 0, 1, all the way to n minus m minus 1. Right here. So 0, 1, all the way to n minus m minus 1. So in this case, it was just 0 and 1, right? Because n minus m minus 1 is equal to 1. Okay, so for Q equals 0, we got 90. For Q equal 1, we got 270. And we stop there. All right. Let's do another one. So let's say we've got the following plant, GP of S equal, let's do just this. S plus 1, S plus 2, S plus 3. So let's keep it nice and simple. Let's just do that. And again, same thing. Let's sketch it on the real axis and sketch the asymptotes. Determine the number of branches, of course. Let's kind of go through this one together and see what we got. Let's do it step by step, and y'all can tell me whether it's matching up with what you're doing or what you expect. Real part of S, imaginary part of S. Very first thing that we do is mark the poles and zeros, poles with an X, zeros with a circle. So here with a circle, I've got -1. Here with a X, I got -2 and -3. And then from here, I am ready to do step one, which is all about the real axis. And I say, okay, let's move right to left over here. Got nothing, nothing, nothing. And then I'm able to fill this part in. Then I leave this part blank, and then I fill this part in again. Okay. Furthermore, I know that here the poles are at k equals 0. And I know that as I turn out my gain, I'm going to leave those poles. Right. So that's from step one. And next up, we determine the branches and asymptotes. So here we know that n is equal to 2 poles, m is equal to 1. So from here, because n is equal to 2, we're going to have 2 total branches. Two total branches. And of those 2, notice that 1 is going to end at a 0. So 1 terminates at a 0. And the rest, in this case, 2 minus 1, which is 1, is going to terminate at infinity. And we know that, let's say a long asymptote. So again, when we say at infinity, it could be way up here or down here or here or here or in any direction. So we're going to have one branch that terminates at a 0, and the rest, the other one, is going to terminate at infinity. And notice that it's also kind of already done for us right here. We can verify with the formula, but it's almost done for us because in step one, we saw that this thing started here, and hey, look, it finishes here. So we already have one of the branches already. So this 0 is where, as k goes to infinity, that's where we're going to end up, at that 0 right there. So this is one of our branches. And in fact, notice that the other branch was already done for us too, right? Because we've got this thing that starts here and goes on forever. So this right here is going to be your other branch. Now, so you really, we're already set up for the asymptote step if we want. We can verify with the formula. So if it's true that this is right, if I do my sigma A, so this is again 2q plus 1 over n minus m times 180. Notice this should give me 180 because this is going out here with an angle of 180. And so here I've got n equal 2, m equal 1. I've got q all the way from 0 to n minus m minus 1, so just add 0. Therefore, I got 2 over 2 times 180, which is equal to 180. So indeed, my angle of my asymptote is going to be 180, which completely checks out with what I have already drawn. So that's great. Notice the center of the asymptote, this sigma A, doesn't really matter a whole lot. You can do, but again, it's that 1 n minus m, then some of the poles minus some of the zeros. So here, n minus m is going to be 2 and 1, so 1 over 1. And then some of the poles, we've got -2, -3. And then the 0 is going to be -1. So -2 plus -3, -5, minus -1, -4 again, right? So it's going to be -4. So basically, over here, I'm going to have, out here, I'm going to have my sigma A, and my asymptote is going to be, and honestly, the sigma A didn't really matter. Like anywhere in the axis, you would have ended up with something along 180, along this line, right? So here we can see that indeed, this line out here is going to align with this asymptote that we expected. So nothing terribly surprising there, but it's kind of nice to have the verification. All right. So any questions with this one? All right, let's do one more and then we'll move on to steps 4 and 5. Same thing, all I want you to do is to sketch the real axis and those asymptotes. So let's say I've got this this plant, GP of S. Let's say it's 1 over S, S plus 1, S plus 2, S plus 3. Okay, let's go ahead and try that out. So let's get this going. As usual, real part of S and imaginary part of S and my horizontal and my vertical respectively. I mark my poles with an X, zeros with a circle. Here I don't have any zeros, but I do have 4 poles at 0, -1, -2, -3. So at k equals 0, that's where I'm starting. And again, I move right to left. You got nothing, 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 and then I'm to the left of one thing. So I fill in this bit. To the left of 2 things, so I'm going to leave this bit blank. And to the left of 3 things, I'm going to fill in this bit right here. And then leave the rest blank. Good. We know that we are leaving we're always starting at the poles. So from k equals 0, this is going to be leaving, this is going to be leaving, this is going to be leaving, this is going to be leaving. So it looks like in both cases, they're going to meet up and split up. Okay. And next up, let's proceed with the total number of branches and so on. So notice we've got poles n equal 4 poles. Therefore, this means we've got 4 total branches. And we've got m equals 0. This means that of the 4 total ones, 0 end at zeros. And the rest, 4, end at infinity. Right? And so our next thing is going to be to apply our formulas for where and infinity. So let's look at the formulas for center and angles of the asymptotes. So our sigma A, 1 over n minus m times sum of poles minus sum of zeros. Okay. And this is 4 and this is 0. Let's see. What is this? Negative 1.5. Negative 1.5 right there for this one. You plug in your formula and apply that. And then using your other formula right here, your phi sub a, that's going to be 2q plus 1 over n minus m times 180. And here again, n is 4, m is 0, q goes all the way 0, 1, all the way to n minus m minus 1. So in this case, it's 0, 1, 2, and 3. right? So if we do that, down here, I'm going to have, yeah, so plugging that in, let's see, should be 45, right? Should be my first one. Then the next one is going to be 135. Okay. Then 225, correct? And 315. And correct me if I made any math errors, but I think that should be correct. Okay. So again, just applying our little formula. Therefore, we can go up here and see, look, our sigma A, let's sketch where it is. It's actually negative 1.5, so it's actually not on the locus, but that's totally okay, it doesn't matter. This is our center of the asymptotes, sigma A. And from there, we're going to have asymptotes at these angles, 45, 135, 225, and 315. So 45, 135, 225, and 315 like that. Okay. And so actually here we can suspect what it is that probably happens. We don't know the exact shape of it. And if you wanted to know the exact shape, you can always use MATLAB. But notice that here, we know these guys are getting together and probably doing something like this, probably like splitting up to go this way and splitting up to go this way. And then these guys probably split up this way to go over here, split up this way to go over here, and kind of line up with those asymptotes towards infinity. So that's what we expect as k goes to infinity out here, k goes to infinity up here, k goes to infinity down here, k goes to infinity up there. Okay. So looking at this one, we might have a couple of questions. So I think it's nice that we've got we've got the general shape of it. Even with doing some very, very basic math, we could get the general shape of it. But you might have a couple of questions. It's like, all right, so where let me see why this happened. I got a call that I'm going to refuse. Okay. There we go. Okay. So a little technical glitch there, but no worries. So notice we might have a couple of questions. So we might say, wait, where does this, does this leave in the middle? Like where does it split up? Like we know that they were coming together at some point and then they split up. Same here, like they came together and then they split up. So where does that breakaway happen? Might be one of the questions that we ask ourselves. And the other is about imaginary axes crossing. So notice that that's a big thing. We know that when this crosses over to the left, we're going to be unstable. So you might wonder, wait a minute, for this one, it's definitely going to happen at some point. For this one, we know that this is going to go along these asymptotes here and here. So there's probably going to be a value of k for which things become unstable. So you might wonder, okay, when does it break away and when does it cross this axis? Those are the key points. And if you look back at steps 4 and 5, you're in luck because indeed that's what steps 4 and 5 are going to be all about. But at least steps 1 through 3, I think we've got those down pretty good. So let's move on to steps number 4 and 5. And step number 4 is all about the breakaway point. So this is when you've got things on the axis when you've got things on the axis, and then you know that they're going to go to an asymptote elsewhere, either up at infinity, down at infinity, wherever. But they're going to break away from the axis at some point. So let's say if GP of S, so this is the plot, is let's say N over D. Let's say the breakaway point is SB. Let's call it SB. That's going to be our breakaway point. And how do we find the breakaway point? Well, we do this little formula. It's going to be ds, d of s, so this is denominator, times n prime of s, minus d prime of s, times n of s, equals 0. So we've set up that formula, solve it. From there, I'm going to get my SB. Okay, so that's going to be where it breaks away. Sometimes this will coincide with that sigma A, with the center of the asymptote. Sometimes it will. Most of the time it won't. Just depends on your specific transfer function. And you might also wonder about, well, the breakaway gain. So at what gain does this happen? Let's call the one KB. So this is going to be the gain at which the poles break away from the real axis. And KB, we've got a simple little formula for that. It's minus D of SB over N of SB. And it turns out this is due to what we just wrote above. This is also, if it's easier, it's minus D prime of SB over N prime SB. So either of those is going to give you your answer. Okay, so there's a couple little formulas there to determine exactly where you are breaking away from the axis. In a lot of cases, it ends up being towards the middle, depending on what poles and zeros you have, but this will give you the exact gain and the exact point at which you break away. And then finally, number 5. So step 5 is to determine the points at which the locus crosses that imaginary axis. And notice this is important because this is, in other words, this is when system becomes unstable. So we want to determine when the system crosses over to the right. So how do we do this? I'll give you a hint. We're going to use a technique we already know from a previous chapter. Can anyone type into the chat and tell me what technique might we use to determine these points? You might need to look back at your notes. So something from a previous chapter that we're going to use right here, going to come in pretty handy. Pablo tells me RH. So, this is This thing with young people, they just give you acronyms, it's like BRB, WTF, RH. Yeah, I mean, they can figure out that lingo. But Paulo, I'm gonna assume you mean good old Ruth Hurwitz stability criterion, indeed. So Ruth Hurwitz stability criterion. So that was the criterion where we would do exactly that, right? So that was going to give us exactly where a system became unstable. It was going to give us the points of marginal stability. It was even going to give us the values of K for which that happens. So this was, again, just recall from chapter 6. And RH, I mean, that's a good acronym to throw into your text conversations. If you're getting to know someone, you want to seem cool, you're flirting a little bit or whatever, and you're like, oh, throw in LOL, RH, it's good stuff, good stuff. So I don't know, it's something you can incorporate to just, I don't know, surely control system's going to help you become popular and socialize, make more friends, right? Hunter's like, yeah, that's what I do. So excellent. All right, folks, so we've got all of them at this point. We've got those 3 steps that we practiced a good bit. And then these 2 are honestly, they're about refining the graph a little bit. So we already have the general shape. These are just going to let us refine the graph, know exactly where it's going to break away, exactly where it's going to cross the axis. One important thing, so we apply Ritz-Horowitz stability criterion, but to what? So we apply Ritz-Horowitz to the denominator of the closed loop TF. Now, this is important because in just about everything we've done before, we have applied it to the open loop. So everything that we've done in terms of setting the whole thing up, we would just use the open loop plant. We were just using the open loop plant steps, all the previous steps within the open loop plant. But then this last one, to determine the like where it crosses, you take the denominator of the closed loop transfer function. So that's important. All right. So tell you what, since we've got all this, I'm going to give you an example, and y'all can get started. Just do it from the top. I'll give you a few minutes to get it started. Then we can walk through it together and see if we can, do all of the steps for a particular system. So let's do this example right here. Let's say I've got good old reference input coming in there. Let's say I have a controller. Let's do this. Let's say the controller is of the form K over S. K over S. So that looks a little tricky. We used to just have K there. And over here, my plant, it's going to be 1 over S squared plus 3S plus 2. I'm going to have Y. I'm going to have good old negative unity feedback. So this coming back here, minus plus. All right, so they're trying to trip us up with a different shape of controller there. And they want you to sketch the root locus. Sk varies from 0 to infinity. Okay. So give this one, think about this one for even before we go through steps 1 through 5. let's think about how might we deal with this slightly different shape of having controller k over s and so on. So I'll give you about a minute or so to think about it, and then you can give me some suggestions on how do I get started with this. Okay. So how about like if you're at home, you can just unmute yourself and give me a suggestion, or if you're here, you can just blurt out a suggestion vocally. So we've done only examples where I had a k here. I've got this k over s. So what do I do? Am I screwed? I mean, am I really just SOL that I've got no methods here for this type of situation? Or can I adapt it a little bit? And if so, how would I do that?
I mean, those two things are being multiplied together, right? So can't we just pull that one over s and basically put that in the plant?
Yeah, so that's great. Thank you, Andrew. So you're basically pretending that this S is actually part of the plant, right? So even though we've got K over S right here, we're isolating the K as that's just the main parameter. And then everything else we are incorporating as if it were the quote unquote plant. So again, we are considering, so consider the, let's say if I'm calling this GC and GP, we want 1 plus GC GP equals 0. So this is because this right here is my denominator of the closed loop transfer function. Right, that's my denominator of the closed loop transfer function, right? So 1 plus GC GP equals 0. And so I set up 1 plus K over S 1 S squared plus 3S plus 2 equals 0. And therefore, I'm in this format where I got 1 plus K times something equals 0. And so everything else, we're going to take this part as if that's going to be our quote unquote open loop plant. Exactly right. Great suggestion. So this is how we handle things in cases like this, where we've got here a slightly different situation, and it wasn't too difficult to kind of pull out that K, and everything else is going to be our plan. There might be some situations that we're going to see where it's even a little bit trickier, where the parameter might be down here in the sensor, or we might be given a closed loop thing, and they're going to ask us, hey, could you tell me how this thing changes as this parameter varies? So whenever that's the case, we want to go back to this. 1 plus parameter times something equals 0. And then whatever that something is, we treat that as our open loop plant. All right. So great. So that's a slight little modification that we cleverly circumvented. So let's get it started. Give you a little bit. Just for reference here, I'm gonna call this GC1 and GP1, but my open loop plant is going to be this thing. So I'm going to call that going forward GP of S. That's my open loop plant, and it's going to be 1 over S times S squared plus 3S plus 2. So notice we've started everything by marking the poles and zeros of the open loop plant. So you probably want to factor this out. I mean, certainly you want to factor this out. So you're going to have 1 over S and then S plus 2, S plus 1, right? Do you guys see why we have this as a quadratic term can't really proceed? We need to mark the poles and zeros of that open loop plant. And so we ended up with this thing right here, 1 over S, S plus 1, S plus 2. Okay. I'm gonna use a new piece of paper and do it fresh on a new page. So we can sketch it down here. I'm going to sketch it nice and clear. So we of course have real part of S in the horizontal, imaginary part of S on the vertical. And we begin by marking the location of the closed loop poles and zeros. Here we've got no zeros, but we've got those 3 poles, 0, -1, -2. We know that that starts k equals 0, k equals 0, k equals 0. That's where we start. Then we can move right to left, filling in the areas of interest. This is blank, and this gets filled in. We know that we are leaving from these areas, leaving from this areas. Leaving for k equals 0, so as we turn it up, it's going to move this way, and these two are going to move towards each other. So already this suggests to me that there's going to be a breakaway point somewhere in the middle there, and that it's going to break away from there to asymptotes. This one seems to stay here the whole way, so that's interesting. So let's move on. So this is step 1 right here, was doing the real axis stuff. Step 2 was determining 2 and 3 was branches and asymptotes. So notice that here n is equal to 3, m equals 0. So from there we've got 3 total branches. And of those, 0 are going to end at the zeros. And the rest, that means to say all 3 end at asymptotes. I guess along asymptotes would be a better way to say it. At infinity along asymptotes. So we can go ahead and do our little formula there for our asymptote. So we've got sigma A. So that's 1 over n minus m times the sum of poles minus sum of zeros. And then my angles of my asymptotes, 2q plus 1 over n minus m times 180. Okay. And so let's see what we got for these. Notice that again here, my n is equal to 3, m is equal to 0, q goes all the way from 0, 0, 1, 2. Q is going to be 0, 1, 2. So again, 3 and 0, and here you got your poles and your zeros. So let's see, I'll give you what I've got in my notes if I wrote it down. Did I? Okay. My sigma A, and y'all can verify it, I got -1 for sigma A, great. And then my angles, I've got 60, 180, and 300. Good. Okay. Great. So now I am ready with this information to sketch my asymptotes. So my sigma A, we said it's a -1. Notice it actually coincides in this case with one of the poles. Yeah, sometimes it will, not all the time, but here it does. So that right there is my sigma A, a -1. And then from there, my asymptote 60, 180, and 300. So 60 is going to do something like this. 180 is going to do something like this. And notice that confirms that indeed, this thing that we had along the real axis, indeed, it was going to be one of the asymptotes, which is great. Just confirms we were doing things right. And then this here is going to be 300. So we got 60, 180, and 300. Should do them a little bit darker so y'all can see them in the zoom. And out here, the third one. Okay, so already I've got steps 1 through 3 taken care of. Let's go into step 4, which is my formula of D. So for let's find SB. So this is number 4, which is the breakaway point. And for that one, I'm going to use the formula of D n prime minus n d prime. So notice here, n was equal to my numerator, 1. D was this thing down here. D was s plus 1, s plus 2. Right, so that was my n of s and d of s were these. And I'm going to then apply this formula right there. So my n prime is the derivative of that. So n prime equals 0, right? And then d I would multiply through. So multiplying through, I get s cubed plus 3s squared plus 2s. Just multiplying that through. And then deriving d prime. It's going to be what, 3s squared plus 6s plus 2. Okay. So then if I apply this to these formulas, notice this part actually goes away because n prime equals 0. So this disappears, n equal 1. So from this formula, I get the following. I get minus n times d prime. So minus 3s squared plus 6s plus 2 equals 0. And that's going to spit out my SB. Okay. Now, y'all can check my math, maybe put it into your calculator to verify it. In my notes, I've got 2 answers, right? When because obviously it's a quadratic formula. And so I have this minus 0.423 as one of them, and minus 1.577 as my other one. And I see some folks telling me, yep, that's what we got as well. All right, so that's 2 solutions, but we only have 1 breakaway point. So what do you guys think? Which one is it going to be? Is there a true one and a phony one there? Okay. So Yeah, just type real quick into the chat, like which one is the actual one of these two. Okay, so Jeff and Hunter both agree that negative 0.423 is the actual one. Indeed, it's going to be right here. This is going to be the one that we take, and this one we are going to reject. And why is that? Well, we come out here. Obviously, the breakaway point needs to lie on the locus, right? And so negative 0.423 is going to be right there. So that's my SB, negative 0.423. That's going to land on the locus. And the other one, the negative 157, is going to be there. Obviously, that cannot be true because we don't have any locus there. Okay. So indeed, that's where we are going to break away. So things are moving towards each other, and at 0.423, they break away, and eventually they're going to go along to those asymptotes. So here, they're going to come together and then do this. All right. Now, let's see what else we got. The KB. So KB is our breakaway gain. And so I can do KB as minus D at SB over 1. And I have to use this formula because this one, like the other one, would have given me a 0 in the denominator, which would have been a pain in the butt. So with this one, I've got this thing is 1. And then I would evaluate this thing right here, D at SB. And I'll save you the calculator work. This is going to be 0.385. 0.385. So this is applying our formula right there. So indeed, right there, KB equals 0.385. Okay, so that's the gain. As I turn the gain up, this is the gain at which things are going to meet, and then they're going to split up. Great. And then the very last step was seeing where it was going to cross the imaginary axis and for which gains. So for that, you would set up your denominator of the closed loop transfer function and apply Ritz-Hurwitz to it. I'll do that in a fresh page. So your denominator of your closed loop transfer function, that is to say your closed loop characteristic polynomial. After I set it up, this is what I have as my polynomial. It's going to be s cubed plus 3s squared plus 2s plus k. Okay. So hopefully y'all got the same thing. Once you got that overall transfer function, check out its denominator. That's what it should be. Okay. Let's see some folks saying, yep, that's what we got. And then we do a good old Ritz-Hurwitz criterion. So remember for that, we got, what we would do is set up our grid here with s cubed, s squared, s to the 1, and s to the 0. Classic Ritz-Hurwitz. This is a coefficient of 1, basically right there. So just remembering how we did this, along the top, I would have this coefficient and this coefficient. So 1, 2. Then in the bottom, I have 3 and k. Right. And then for this one, I would do this times this minus this times this over this. So I would do 6 minus k over 3. Okay. Then for this, there's nothing because I've got nothing to the right of it. And for this one, I would do this number times k minus 0 times 3 over this number. So this times k over this, which this cancels and I get k. Right, so notice that this is going to be stable as long as everything is of the same order. So, or I'm sorry, of the same sign. So here I've got positive, positive. So this needs to be positive, and this needs to be positive as well, right? So it's going to be stable for k positive, and this thing right here, and 6 minus k positive. Okay. That is to say, we can combine these two and to say it's going to be stable between 0 and 6. So already we know that the point that's going to give us problems, or where it's going to cross over, is for k equals 6. So this is going to happen at k equals 6. This crossing is going to happen at k equals 6. And if we wanted to know, okay, yeah, so it's a k equals 6, but at what locations? We would use that auxiliary polynomial. So to determine, say, to determine locations of crossings, set up the auxiliary polynomial. So this is going to be the one above the 0. If you all remember from your chapter 6 homework. So we would set up this polynomial right here. So it would be 3 s squared plus k equal 0. This with k equals 6. Right, that one k equals 6. So 3s squared plus 6 equals 0. So, yeah, so I get 3s squared equal minus 6, s squared equal minus 2. So s equal plus or minus j square root 2. So these right here are going to be the crossing points. Again, so these is using techniques from back in chapter 6. So again, if I want to, so this square root is about 1.4, 1.41. So if I want to mark in my graph where this happens, this is going to be at 1.41j, and down here, the other one, s equal minus 1.41j. We've got our full root locus doing pretty straightforward math. You got the full map of how this varies. Great. So folks, that's a thorough example from top to bottom of doing all the steps here for root locus. And we are done with the theory for this chapter. So this is good news. On Thursday, we'll have a practice session. So at this point, I think I already posted the homework for this chapter. And if I haven't, then I should do that. But y'all can check it out. So I've got, as usual, a homework from the textbook plus some supplementary practice problems. As usual, I think the ones from the textbook I think they're going to be a little bit easier, but maybe they're, in this case, they're of equivalent difficulty. There might be some that are a little bit tricky where we have to be clever about how to pull out that parameter so as to manipulate things. So we might run into that. But yeah, but it's going to be, yeah, practice session, whether in groups or individual on Thursday. All right, folks, at this point, I'll let you go. Good to see you as usual. And yeah, take care.